Alright, so today I want to go over section 7.4, which is about integration of rational functions by using partial fractions. In college algebra, we spent a whole section on partial fraction composition. We will use what we learned then in integration, and I'm going to review that anyways. So, but if you need more information about partial fractions, there's you can go back to college algebra and look for the section that's about partial fraction decomposition. So, as an introduction. So basically, if we want to integrate something like this, where it's a rational function where the degree of the top, the degree of p of x, is less than the degree of q of x. Okay, the degree of the top is less than the degree of. So for example, how do we integrate something like x squared minus 1 over x cubed plus x minus 1? Something like this. Okay, I just made it up. Degree here is 2, degree there is 3. So we use what we call partial fraction decomposition unless we can do substitution. Okay, if substitution fails, then we go into this one. So what are the steps for partial fraction decomposition? I'm going to review that, and we're going to blend it in with integration, so you don't feel like if you forgot your college algebra that you're going to lose out. No. Okay, so steps for partial fraction decomposition. Steps for partial fraction decomposition. So our objective is to integrate integral of p of x over q of x d of x. So the first step, if the degree of p of x is greater or equal, so if it's not what we want, then what do? There's a way to get away with this, to divide using long division. To divide using long division of polynomials. And so when we divide, so say I have p of x over q of x. Okay, you divide, you get a quotient. Let's call it L of x. That's the quotient, plus a remainder, and we write usually the remainder over the divisor. Okay, so we take this and use this in step 2. So use r of x over q of x in step 2. So first we want to remove the quotient and use the remainder over the divisor to go into the next step. Okay, because that's going to be easy to integrate. Then we're going to work on this to integrate. So factor q of x. So we factor the denominator q of x completely into linear and irreducible prime factors, prime quadratic factors. So we're going to factor the polynomial at the bottom into linear, like a plus b, and then quadratic, ax squared plus bx plus c, as long as the quadratic doesn't factor anymore. Okay, if the quadratic factors, then you factor it into linear factors. And then the next step is to collect all repeated factors so that the bottom q of x is expressed as a product of distinct or different factors of the form, so ax plus b to the m times, say, ax squared plus bx plus c to the n. So for example, you would have x plus 1 cubed and then x squared plus 1 squared, right? Linear factor. If there's x plus 1 3 times, then you put it to the third power. If it's 2 times, you put it to the second power, and so on. Now, So this is the general, okay? You look at the, so if you're integrating something like x squared minus 1 over x cubed plus x plus 1, and substitution doesn't work, or integration by parts, or what we've done, then you would see if the degree of the top is less than the degree of the bottom. If it's greater, well, you do long division, and then you take the part where the degree of the top is less than the degree of the bottom, and then you act on that. Okay? If that's not the case, so then the next step would be to factor the bottom completely, and then you collect. So you want the bottom basically in prime factored form. Okay, now after doing this, now you follow. So I'm going to show you the next 4 cases of integration and partial fractions. So we were reviewing partial fractions. Now we follow the next 4 cases of integration and partial fractions. So the first case is when we have non-repeated linear factors. So if the bottom has non-repeated linear factors, for instance, if you have something like this, P of x or Q of x equals, so you can see we're always working on the bottom, a1x plus b1, a2x plus b2, a(n)x plus bn. Non-repeated linear factors. These are all different factors and they're linear, no square in there. So all these are, and the degree of the top is as always, the degree is less than the degree of the bottom, and the c's, the a's, the b's are constants. So then you can write p of x over q of x as c1 over a1x plus b1, c2 over a2x plus b2, and so on. So you put constants on top. Why constants? The degree of a constant term is 0. The top will always have a degree less than the degree of the bottom. If the degree of the bottom is 1, then the degree of the top is 0. As you will see next, if the degree of the bottom is 2, then the degree of the top is 1, which means you'll have linear on top. Okay? And then integrate accordingly. So instead of integrating this guy, which doesn't integrate easily, we're going to integrate these individual ones, which should integrate easily. Here's an example. How do we evaluate the integral of 2x plus 1 over x squared plus 2x minus 3? If we try substitution, we need 2x plus 2. We don't have 2x plus 2, we have 2x plus 1. Because if we let u equals x squared plus 2x minus 3, du would be 2x plus 2, which is not going to work. But the degree of the top is less than the degree of the bottom, so we want to try to factor the bottom. It does factor luckily into x plus 3 times x minus 1. So these are distinct linear factors, so we put one fraction for each factor, and we put constants. Instead of c's, I'll use a and b, okay? And the next step is to, so after you split it up, then you multiply by the LCD, and usually the LCD is the one, this guy, the one that you factored. So if you times by the LCD, x plus 3, x minus 1, x plus 3, x minus 1, x plus 3, x minus 1. So that guy is going to appear, and you will have 2x plus 1 equals a times x minus 1 plus b times x plus 3. So now you want to distribute, you want to combine the x terms together and the constants together, factor out the the x, minus a plus 3b. So you can see this is always true, meaning that 2x has to equal a plus bx, and the constant has to equal the constant, okay? So if 2x equals a plus bx, that means a plus b equals 2. We drop the x, and then 1 equals negative a plus 3b. So we get a system of 2 equations solved by elimination. 4b equals 3. So b is 3 over 4. And then to get a plus b is 2. We plug it in. So a is 2 minus 3/4 is 1 1¼ or 5/4. And then we write our integral. Instead of writing integral of 2x plus 1 over x squared plus 2x minus 3 dx, we can write it as a, which is a is 3/4. No, a is 5/4 over x plus 3, and then b, which is 3/4 over x minus 1 dx. So it's 5/4 ln absolute value of x plus 3 plus 3/4 ln of absolute value of x minus 1, and as always we add a constant. Okay, here's another example. How do we evaluate the integral of x cubed is 2x over x squared plus 3x plus 2? You can see here that the degree of the top is greater than the degree of the bottom. So we have to do long division. And if we do long division, x cubed minus 2x over x squared plus 3x plus 2, we will divide x squared into x cubed. We're going to get x. If you times it out, we get x cubed plus 3x squared plus 2x. Switch the signs. That cancels out. This guy has to come down. Minus 3x squared minus 4x. Now divide x squared into negative 3x squared. It's negative 3. So negative 3x squared minus 9x. Plus, so it's 5x and then minus 6 here, so it's plus 6. So this is x minus 3 plus 5x plus 6 over x squared plus 3x plus 2. Okay, so now we're gonna write the integral of x cubed is 2x over x squared plus 3x plus 2 dx equals the integral of x minus 3 plus the integral of 5x plus 6 over x squared plus 3x plus 2 dx. So this we can integrate. That we can integrate. This one is what we're gonna have to do partial fractions. So if we take 5x plus 6 over x squared plus 3x plus 2 is x plus 2, x plus 1. If we factor it out, a over x plus 2 plus b over x plus 1. Again, we multiply by the LCD. We get 5x plus 6 is a into x plus 1 plus b into x plus 2. Distribute ax plus bx. I'm putting the x terms together. So x times a plus b plus a plus 2b, and that should equal 5x plus 6. So 5 has to equal a plus b, and 6 has to equal a plus 2b. Solving this system, we get a equals 4, b equals 1. So this is a 4, and this is a 1. Okay, so now we can integrate. So the integral of x cubed minus 2x over x squared plus 3x plus 2 dx equals integral of x minus 3, which is x squared over 2 minus 3x plus integral of this guy 4 ln absolute value of x plus 2 plus 1 ln absolute value of x plus 1 plus c. Pretty neat, okay? So that's if we have distinct linear factors in the denominator. Next, we're going to look at repeated linear factors in the denominator. So if p of x over q of x equals x over ax plus b to x square, cube, whatever it is, as long as it's more than 1. And of course, we want always the degree of p of x is less than. If it's greater than, you saw what we do first, we do long division. So then we write p of x over ax plus b to the n. We write c1 over a. So we want to put a constant for every possible power. So first power, second power, and then the nth power. This is 2. Okay, so we have to put a constant on top of each possible power from 1 to n, and then integrate accordingly. Then integrate accordingly. So example 3, evaluate the integral of x squared plus 2x plus 4 over x plus 1 cubed dx. So the degree of the top is 2, the degree of the bottom is 3. So we have that requirement, and we have a repeated factor, so we're going to split it up as we just talked about. We're going to put a constant for the first linear factor, constant for the square factor, and then a constant for the cube factor. And then we times by the LCD, which is, again, sometimes I'm not writing it, x1 cube, x plus 1 cube, x plus 1 cube, x plus 1 cube. So we're going to get x squared plus 2x plus 4 equals, one of these is going to cancel out, x plus square, which is x squared plus 2x plus 1. This is b times x plus 1, which is bx plus b, and this is just c. So distribute this guy, plus 2ax plus a plus bx plus b plus c. So you can see we have quadratic, we have linear, we have x, which 2a plus b, and then we have the a, the b, and the c, which is the constant. So x squared is going to equal x squared, 1 is going to equal a, so we already know the value of a, 2 is going to equal 2a plus b, so 2 plus b equals 2, so b is 0, and c, 4 is going to equal a plus b plus c, 1 plus 0 plus c, so c is 3. So let's put all these values. A is 1, b is 0, so we're not going to have a square term, and c is 3. So the integral of x squared plus 2x plus 4 over x plus 1 cubed dx is the integral of a is, what did we say a was, 1 over x plus 1 dx. B is 0, so there's no need for that, and c is 3, x plus 1 cubed dx. So it's ln absolute value of x plus 1. And now x plus, the 3 comes out, x plus 1 cubed is x plus 1 to the negative 3 on top, which you add 1, you get negative 2, divided by negative 2, which is times negative 1/2. So plus c, so it's ln absolute value of x plus 1 minus 3 over 2, x plus 1 squared plus c. Okay. Here's one. Example 4. Evaluate integral of 6x minus 1 over x cubed. So you can see here 2x minus 1 shows up once. X is a factor, it's a linear factor, shows up 3 times. And the degree of the top is less than the degree of the bottom, so we're going to do this. X cubed 2x minus 1. So the x has to show up 3 times, x squared, and then x cubed. And then 1 time for 2x minus 1. Okay, 1 for 2x. So we're going to times everything by the LCD, which is always this guy. X cubed times 2x minus 1. X cubed times 2x minus 1 for each one of these guys. X cubed times 2x minus 1. X cubed times 2x minus 1. That's going to cancel out everything, all the denominators, 6x minus 1. This would be ax squared 2x minus 1. This guy would be bx times 2x minus 1, c times 2x minus 1, and then dx cubed. So we have a lot of terms to collect. So we have 2ax cubed minus ax squared plus 2bx squared minus bx plus 2cx minus c plus dx cubed. So we're going to put the x cubed terms together, the x squared terms together, plus 2b minus a x squared, and then the x terms together, plus 2c minus bx plus or minus c. So there's no x cubed and there's no x squared, so we're going to put zeros for those, okay? And then plus 6x minus 1. So 2a plus d equals 0. 2b minus a plus 2b equals 0. 2c minus b equals 6, and negative c equals negative 1. So this tells me that c is 1. Go back here, that means b is negative 4, and then you can get a from here. A is 4, b is negative 4. Wait, 2b minus a, why did minus a, that should be 2b, sorry. So a is negative 8, sorry. And then d is 16. So you have the integral of 6x minus 1 over x cubed times 2x minus 1 dx is integral of a, which is negative 8 over x, plus b. b is negative 4 over x squared, plus c dx. c is 1 over x cubed dx plus d. d is 16 over 2x minus dx, which is now easy to integrate. Minus plus 4 over x minus 1 over 2x squared plus 8 ln absolute value of 2x minus 1 plus c. Alright, so we've done linear factors, whether it's distinct or repeating. Then we're going to do quadratic. Number 3. We're going to talk about non-repeated, irreducible, means they're prime, quadratic factors. So if you have that, p of x over q of x, then we write, if it's all quadratic, like ax squared, a1x squared plus b1x plus c1, a2x squared plus b2x plus c2, and so on, an. We write this as, so we're going to have a linear up there, okay? Because the degree of the top is going to be always 1 less than the degree of the bottom, okay? And then a2x plus b2 over a2x squared plus b2x plus c2, and so on. Degree here is 1, degree here is 2. Okay? So how do we evaluate, as an example, the integral of 4x over x squared plus 1 times x squared plus 2x plus 3 dx? Well, the first quadratic factor is prime. The second one is factorable. No, it's not. Product of 3, sum of 2. Forget it. So they're both non-factorable, which is good. Okay, prime. So we're gonna write this as ax plus b over x squared plus 1, cx plus d over x squared plus 2x plus 3. And then we multiply by the LCD, which is gonna be this guy, x squared plus 1, x squared plus 2x plus 3. Same thing here, x squared plus 1, x squared plus 2x plus 3, x squared plus 1, x squared plus 2x plus 3. That cancels all that out, and you get 4x equals ax plus b times x squared plus 2x plus 3 plus cx plus d times x squared plus 1. So we're gonna work it out. So 4x equals ax cubed plus 2ax squared plus 3ax plus bx squared. I'm gonna line up like terms. Bx squared plus 2bx plus 3b, and then over here cx cubed plus dx squared, plus cx cubed plus dx squared plus cx plus d. So we have a plus cx cubed plus 2a plus b plus dx squared plus 3a plus 2b plus cx plus 3b plus d. Remember, we have 0x cubed plus 0x squared plus 4x plus 0. The constant is also 0. So a plus c is 0, 2a plus b plus d is 0, 3a plus 2b plus c equals 4, 3b plus d equals 0. Solving this, I'll give you the answer. You can work out, it's not hard. And d equals -3, and you can see this is a very long problem. So the integral of 4x over x squared plus 1 times x squared plus 2x plus 3 dx is the integral of x plus 1 over x squared plus 1 minus x plus 3 over x squared plus 2x plus 3 dx. So we can do substitution on this guy, and 2x plus 2 so for the integral of x plus 1, let's do this one first. That's the integral of 2x over x squared plus 1 times 1/2 plus integral of 1 over x squared plus 1 dx. So I split it up. This is substitution. This is half ln of x squared plus 1, and this guy is tangent inverse of x. Okay, that's this guy. Now that guy, the second guy. So with this guy, now let's do this guy. Integral of x plus 3 over x squared plus 2x plus 3. That's gonna equal integral of, so I need, if I split it up, x squared plus 2x plus 3, and then integral of 3 over x squared plus 2x plus 3. This guy I need two x plus 2 if I want to use substitution, right? Or I could do, I don't have to do that here. What I did, I'm looking at what I did in my notes. X plus 3 over x squared plus 2x plus 3. I could write it as x plus 1 plus 2 over x plus 1 square plus 2. If I do completing the square, which would be 1/2 times 2x plus 1 over x plus 1 square plus 2 over x plus 1 square plus 2. So I can work it out this way, and the integral of x plus 3 over x squared plus 2x plus 3 dx is gonna equal 1/2 ln of x plus 1 square plus 2 minus square root of 2 tangent inverse of x plus 1 over root 2 plus c. Okay. Alright, and finally, when we have repeated quadratic prime factors, it's number 4. Repeated, it could get really too much work. Quadratic prime factors. So if p of x over q of x equals p of x over ax squared plus bx plus c to the power n is greater than 1, then we split it up into as many, so we're going to put linear here over the first one, and then linear again to the power 2 at the bottom, and so on, as many as the power, just like we did with the repeated prime. So for example, to evaluate x squared over x squared plus 4 squared, so we write x squared over x squared plus 4 squared as ax plus b x squared plus 4 plus cx plus d over x squared plus 4 squared. And then we times by the LCD, so that's going to give me ax plus b x squared plus 4 plus cx plus d. So if we FOIL this, we get ax cubed plus bx squared plus 4ax plus 4b plus cx plus d, which is ax cubed plus bx squared plus 4a plus cx plus 4b plus d. There is no x cubed, so we put a 0, and there's no x, and there's no constant. So we just have to do what we have. So a is 0, b is 1, 4a plus c is 0, and 4b plus d is 0. So if 4a plus d is 0, c is 0, 4b plus d is 0, and b is 1, so d is negative 4. So we got a is 0, and we got c is 0, so b is 1, and d is negative 4. So we will have the integral of x squared over x squared plus 4 squared is 1 over x squared plus 4 plus negative 4 over x squared plus 4 squared dx. So for this guy, we know what the answer is. Now we're gonna use so this is I1 and this is I2. So for let's use I2 first, it looks more work. Negative 4. So let's just leave the negative 4 out, okay? 1 over x squared plus 4 squared. We use x equals 2 tangent theta. Remember trick substitution. So dx is 2 secant squared theta d theta. And this guy would be the integral of 2 secant squared theta d theta, which is dx. At the bottom we got, so we have 4 tangent squared plus 4, which is 4 secant squared, which is 16 secant to the 4th power. That cancels this guy out, so you get, and 2 that's 1/8, 2 over 16, 1 over secant square, which is cosine square theta. And cosine, remember we change it into the double angle, so we get 2 1/2 1 plus cosine 2 theta, which is 1 over 16 theta plus 1/2 sine 2 theta d theta, which again, if tangent theta is x over 2, opposite over adjacent, then this would be square root of x squared plus 4. So sine 2 theta is 2 sine theta sine theta. Sine theta is opposite over hypotenuse, cosine theta is adjacent over hypotenuse. So we're going to put all this in there. So this is 1 over 16. Theta is tangent inverse of x over 2, right? So tangent theta is x over 2 plus 1/2 times 2 is gone. Sine theta is x over root x squared plus 4 times 2 over root x squared plus 4. which is 1 over 16 tangent inverse x over 2 plus 2x over x squared plus 4, which means the integral of x squared over x squared plus 4 squared is, the integral of 1 over x squared plus 4 is 1/2 tangent inverse x over 2, right? Because you can pull the 4 out, and you get x squared over 4, which is x over 2, okay? And then minus 4 times this guy, tangent inverse x over 2 plus 2x over x squared plus 4 plus 6. And that's it for section